Okay, so far we talk about block ciphers and hash functions, and we use them for two different contexts. For instance, block ciphers provide you confidentiality. You can communicate in a secure way, but hash functions provide integrity. So you check if the content of a publicly known value is changed or not. Okay, but here, when I'm doing encryption, I would like to have integrity too, right? Think about it like this: I have a message to send you, and it is not secret, and I'm sending it to you. But there is a malicious attacker in the middle, and the attacker removes some part of it or modifies some part of it. How would you know? So a message authentication code will allow me to detect this. Okay, so in this case, there is no encryption involved. But the question is, can I combine both encryption and this kind of message authentication so that I provide both confidentiality and integrity? Because think about also communicated in an encrypted way. Assume that I encrypted a 1 megabyte Word document and send it to you in an encrypted way, but the attacker, seeing the ciphertext, couldn't understand what I'm sending to you, but they simply erase some part of it, probably maybe the last part. So when you receive it and decrypt it, the document will also still look like a Word document, but you wouldn't know which parts of it is missing, right? There's no integrity check in the encryption alone. So our motivation here, first to provide authentication, but here we are talking about data authentication. Then, so we will talk about message authentication codes. And we will combine this idea with the encryption and then provide both confidentiality and integrity at the same time, which we will refer to as authenticated encryption. Okay, so let's move on with some definitions to see how this can be done. So we start with message authentication codes. So message authentication codes are not used for encryption. Okay, this is important. It is used for message verification. So communicating parties share a secret key K and then compute an authentication tag T using the secret key. Sender computes T and sends it with the message. So when I'm sending you a message, I'm also sending a small tag. Okay, so you receive the message and the tag. And from the message you received, you also generate the tag following my steps. And now you generate the tag T prime. And you check if T prime is equals to T. If they're equal, this means that nobody modified my message. If it is not, this means that somebody modified the message, so the verification is broken. Okay, so this is how it works. So let me now show you attack types. So assume that I give you n message tag pairs. So in the past, for instance, we communicated n many times. So the person who is listening to the communication captured this n messages and their tags. Okay. So it should be infeasible for an attacker to recover the k-bit secret key K that was used to create these tags. Okay, because we are generating this tag using a secret key, so it shouldn't leak from this data. So this is like trying to capture the secret key of a block cipher. But in this context, the attacker can do something else, which is called forgery. So we call it MAC forgery. MAC is the short for message authentication code. So in cryptography, MAC is always refers to this, but in networks, we use MAC for something else, like media access control. So this is not to be confused with that. So here, attacker might try to do this. So they collect n message tag pairs. So M1 with the tag T1, M2 with tag 2, Mn with tag Tn. Now it should be infeasible for an attacker to generate a valid message tag pair M prime and T prime, where M prime is not a previously sent message. So if you can do that, you forge a message. And of course, if you perform the first attack, meaning key recovery, then you can forge everything, right? But sometimes these algorithms are weak in the sense of forgery. So even if you cannot capture the secret key, you can provide MAC forgery. Okay. So key recovery attack should require 2 to the K operations. Key recovery attack leads to MAC forgery, but for a weak scheme, it may be possible to forge a tag without recovering the key. If the message authentication tag T is of T bits, a successful MAC forgery should require 2 to the T operations. Okay, so let me give some basic examples that use block ciphers. these were some old standards. I'm guessing not many people are using it, but think about like this. So don't forget that message authentication code is not an encryption. My aim is to provide authentication or verification. So you can use a block cipher as follows, like in the CBC mode. Recall that in the CBC mode of block ciphers, you encrypted blocks one by one and produce the ciphertext block here, but also XOR it here. But since this is not an encryption, you do not provide any outputs here. You encrypt this in a serialized way, and then perform a finalization process and produce the tag. So when you send your message M, you send it with this T. So the person you're communicating also has the secret key, so they receive the message. They also perform this operation to obtain their own tag and check if these tags are identical. If they are, this means that the message is not altered. Okay. So last ciphertext block is independent on the previous plaintext blocks in CBC mode. This is the motivation. CBC-MAC appears in some American standards, FIPS 113, with DES being the underlying block cipher. Since DES no longer is a standard, some new standards use this with AES. This final process is to avoid forgery attacks or length extension forgery attacks, because if you have this until this part, somebody might be able to add something more to the end. And then this is not that much used, but people sometimes use CMAC or OMAC. The exact definitions are not that clear in the literature because, for instance, OMAC has two variants, but the first variant, OMAC 1, is identical to CMAC. So I'm generally confusing which one is which. But CMAC fixes security deficiencies in CBC-MAC. So it is same as CBC-MAC. But also you, at this top part where you use some tweaks, combine it with your last message block and provide the output. Okay. Now I'm assuming that this is what CMAC is. But more importantly, this is the one almost everybody is using, and this is the one that you might observe on the wild, okay, called HMAC. The previous ones I talk about, this E here, or E-enc here, was encryption, so you use the block cipher. Now we will use a hash function. So HMAC is actually short or hash-based message authentication code. Okay. So when you have a message M, you send it to the person you are communicating, but you also assign it to a tag like this. Okay. So idea is as follows. You choose a hash function, for instance, SHA-1, and this is what your actual router at your home is doing. They use HMAC SHA-1. Okay. Now you have the message M here and your secret key K here. You XOR it with something fixed called iPad. It's just a repetition of the same bytes. It is not secret. You can even find it on Wikipedia. Okay. You XOR it with iPad and then concatenate it to your message. Okay. Then calculate your hash. So it doesn't matter how large your message is. This output is small. Then you reconcatenate your secret key again, but this time you XOR it with something else in order to break the symmetry here. And put it in another hash, put it in the hash function for the second time and obtain the output. Okay, this is your tag. And this is what many protocols on the internet is using, like your router. When you choose a password for your modem at home, from your password, the secret key of AES is generated using this algorithm multiple times, generally 4,096 times. Okay. So, of course, one question is, do we need the calculation of this hash function twice? What happens if I remove these parts? As far as I know, it's still secure and there is no attack rate. Okay. But it was designed like this to prevent some, problems, and this is what people generally use for message authentication code. Okay, so again, you can use, for instance, SHA-256, and WinRAR uses SHA-256, by the way. So you put your message here, concatenate it to, at the beginning you put your secret key, XOR with iPad, concatenate it. So even if this part is really large, this part is small. This is because if you are using SHA-256, this is 256 bits. You XOR it so concatenated with this, and the second part is generally easier to do compared to this part because the other input is small. Okay. So these are the main message authentication codes people use. At the lightweight side, ISO also has standards for this message authentication code. So following algorithms are specified in ISO standard that is defined in 2019 for lightweight message authentication codes. These are LightMAC, Chaskey, Tsudik, and Tsudik's Keymode. LightMAC is something like this. So designed by Luix, Prenel, Tischhauser, and Yasuda in 2016. There is something called PMAC, by the way, but it is patented. So LightMAC is not covered by patents because it's based on Bernstein's protected counter-sum mode. So what they do is you divide your message into blocks like M1, M2, M3, but you also at the beginning put some counters, and this is how you perform the encryption. Perform the padding in your last message block. Finally, perform another encryption. And if the output should be smaller than your block size, you perform a truncation operation here and produce the tag. Okay. So this is based on a block cipher. So you have to choose what the block cipher you want to use here. Okay. Chaskey, this is efficient MAC for 32-bit microcontrollers. It was designed in 2014, 10 times faster than AES 128 in CMAC mode on a ARM Cortex-M. Bottom image is for when the message length is a multiple of block size, so you don't need to perform any padding here. But if there's a padding has to be done, the top picture is used. So your secret key, 128-bit K, is kind of divided into two as K1 and K2 here. Okay. So there is a pi operation here. As you can see, it is a permutation and it is this. And this is applied 12 times. As you can see, the operations are simple: XOR, addition, rotation. So they also provide some benchmark results on this processors like Cortex M0 or M3 and 4. So they compared with AES in the ECB mode and CMAC mode. And here are the results. For instance, here at the ROM size, Chaskey requires less. And speeds, this is cycles per byte, meaning that how many cycles you need to encrypt or process a single byte. This means that smaller is better. Okay, so this is why they say that they are 10 times faster than AES. As you can see, they also require less memory to perform. So these are speed optimized. These are size optimized. Yeah, another one is Tsudik's Keymode. This is very simple. This is why it was designed in 1992. Even it is very hard to find the original paper from the IEEE webpage. It is like not the original paper, but it looks like a scanned document. I found it and looked at it and tried to discover what it says. So it uses a hash function instead of a block cipher. Security depends on the security of the used hash function. And idea is really, really super simple. So when you have the message and the secret key, simply concatenate both of them, calculate the hash of this, and provide the tag. Okay, and that's it. Okay. And when you communicate, you send this tag with your message to the person you're communicating. And the person who has the secret key also receives this message, concatenates it, obtains the same tag. If they don't obtain the same tag, they say that it is modified. So this is the secret suffix version, and there's the secret prefix version. So you simply swap the places of key and the message. And it works. As far as I know, nobody found an attack to this. But of course, if your key is short, somebody can brute force it this way, right? So it depends on how fast you can calculate the hash if the key is short. But here, generally we don't like this kind of stuff. If you concatenate this kind of stuff as an input, But we want to be sure that what is the domain separation, which part is the key and which side is the message. Because if the system allows to use longer keys, a long message with a short key might give the same output with the short message with the longer key, because by chance they might be using the same bits, right? So this is why generally we put a separator called domain separator in this kind of operations. So as far as I know, none of them are broken and these standards remain the same. Okay, any questions?